All right, so here we go. Oh, already down to the end of the page. Here we go. Here's the proof for the fundamental theorem. Okay. So we're going to start out with our difference quotient without the limit. I'll put the limit in here in a little bit. Let's look at g of x plus h minus g of x all over h. Okay. The first thing I'd like to do is let's go ahead and just rewrite this slightly. Let's write it as 1 over h times g of x plus h minus g of x. Everyone see what I did there? I just pulled out the 1 over h in front. Okay. Okay, but what was g of x? I hope you know this function. I hope you know this function. You've been working with them for 2 weeks now. I hope you know this function. This is the function that goes from a to x plus h of f of t dt. That is g of x plus h. What did I do? I took g of x. I took g of x, and everywhere I saw an x, I plugged in an x plus h. Minus just the regular g of x, minus the integral from a to x of f of t dt. Any questions on that? All right. So this is equal to 1 over h times, and now I'm going to do something a little sneaky. Okay, you've seen me do this a couple times. I'm going to rewrite this as the integral from a to x of f of t dt plus the integral from x to x plus h of f of t dt. That all is this underlying portion right there, and then I still subtract off the integral from a to x of f of t dt. And one way to look at that is if I had this picture right here. Here's my f of t. And it doesn't have to, the picture doesn't have to work out this way, but it's easier to draw if it does. If I want to go from a to x plus h, what could I do? If I want to find the area underneath the curve from a to x plus h, I could stop off at x, right? And I could find this area first. That would be the area from a to x. And then add to it the area from x to x plus h. Add up from a to x, and then from x to x plus h. Well, that's kind of nice, because now one of those terms sort of cancels. I don't know if we've made the problem easier or not, but now we're down to 1 over h times the integral from x to x plus h of f of t dt. Okay. Folks, is this the derivative? What do we start off with? We start off with this guy right here. Is this the derivative? Is this how we calculate the derivative?
Yeah.
It's the difference quotient. The derivative has a difference quotient in it, but is this a derivative? Everyone say no, it doesn't have limits. All together.
No, it doesn't have limits.
No, it doesn't have limits. Can you have a derivative without a limit?
No.
Well, not necessarily. So what I need to, I can always calculate this difference quotient, but what do I need? I need h to go to 0 for this to actually be the derivative, right? So I haven't taken the limit yet. Okay? So we want to find all that remains. So all that remains is to find the limit as h goes to 0 of 1 over h times the integral from x to x plus h of f of t dt. Folks, I had a bad day the other day. My head wasn't working. I was working through this proof again. I've done this proof about a dozen times. Working through it again. And I actually had an idea. It was really nice, and it kind of cleared up my head. I've said that all of calculus is built on these indeterminate forms. All the big ideas in calculus are built on indeterminate forms. Is this an indeterminate form? How come? Sure, we have something divided by 0. That's not an indeterminate form, right? 3 over 0 is not an indeterminate form. It's just flat out undefined. So that's not indeterminate. What is an indeterminate form that's kind of like that? 0 over 0 is an indeterminate form. Is this an indeterminate form, 0 over 0? No. Is it? This was my idea. Kind of excited about it. Sharing it with you. If I did direct substitution here, I'd have a 0 here in the denominator, which you can't do, right? I'm just looking at the form. I'm looking at the structure. I have a 0 in the denominator, and I put a 0 up here. That would leave me with the integral from what to what? X to x. What is the area underneath the curve from x to x? 0. So this whole quantity is tending toward, this whole quantity right here is tending towards 0. As is the thing I'm dividing it by. I know I didn't put the divided by down here because it's a little strange to put an integral in a numerator of a fraction. But this is still an indeterminate form, 0 over 0. It's still an indeterminate form, so that we didn't get away from them. Since day one, we've been dealing with indeterminate forms. Okay, so all that remains is to take this limit, but whew, good luck. I don't know how to take that limit. Okay. So what are we going to do? We're going to play catch the cat. What do? You got a cat running around that you're trying to catch, so you start boxing it in, boxing it in, boxing it in. Okay. What do we know about the area underneath any curve? Well, we know that it's less than the area of its minimum rectangle that it could be fit into, and greater than the area than its minimum rectangle, and less than the maximum. Thank you. So what do we know? We know that this area right here, from x to x plus h, the area of this curve, now notice I don't have the over h yet. We know that this is less than the minimum times h, which is less than or equal to the maximum times h. Why did I put h as the width of that? Because what's the width of this interval? It goes from x, let's do a different color. It goes from x to x plus h. How wide is that? It's h wide. So this is the base of the entire region. And so that's that minimum rectangle. That's that maximum rectangle. Going back to this picture right here. It's the exact same property. It's just being applied here. I've got x and x plus h, but it's the same idea. Okay. Now, we have one condition on f. What is it? What is the one condition we impose on f? That it be what? Continuous. It be continuous. We've got a closed bounded interval. We've got a maximum. We've got a minimum. We need to guarantee that f actually achieves its maximum and minimum. Okay. By the extreme value theorem, since f is continuous, there exists a u and v. Those are two separate things. Let me say it like this. There exists, let's say it like this, a u contained in x to x plus h, and a v contained in x to x plus h, so that f of u equals little m, and f of v equals capital M. Why does this work? Since f is continuous. So the extreme value theorem says any function on a closed bounded interval will actually arrive at its maximum and minimum. There's some input values that guarantee you'll get output the maximum or minimum. Okay? So if you look at this picture here, what I'm saying is I would call this my u. Why? Because what's f of u? The minimum. And I would call this my v. Sorry, let me not put it up there. I would call this my v, right? Because this is the order pair v comma f of v. And what is it equal to? The maximum of the function. How do I know I can do that without even knowing what this function is? Because I do know it's continuous. All right. So returning to that, this statement right here, this line. Okay. So I can rewrite this line as f of u times h is less than or equal to the integral from x to x plus h of f of t dt, which is less than or equal to f of v times h. So all I did was replace the maximum and minimums with the actual output values in the function. So close, folks. I'd now like to divide all three sides of this by h. Here I need to make an assumption. H does not equal 0. And let's assume, without loss of generality, without loss of generality, assume h is positive. Okay. This proof works just fine. It works the exact same way. If you assume h is negative, you just have an extra step. But you have to pick one, because I'd now like to divide this inequality by h. And whenever you divide an inequality, the resulting signs on the inequality, that depends on the sign of the number you divided by. So I want to go ahead and just assume that it's positive. H is positive. So when I do so, I get f of u is less than or equal to 1 over h times the integral from x to x plus h of f of t dt, which is less than or equal to f of v. So the minimum value is less than this quantity, which is less than the maximum of the function. Okay, does everyone see what I did here? I just divided this h into each term. Okay. How come I knew I could leave the direction of the inequalities the same? Because I assumed that h was positive. Now, if h were negative, what would I have to do? I'd have to change the direction of this sign, I'd have to change the direction of this sign, but what else could I do? Well, this is the smaller quantity up here, and this is the larger quantity, so I would then invert it. So I would invert these two, give myself another negative, divide that other negative through, and I would eventually get back to this expression that we have. So it doesn't matter whether it's positive or negative, it's just if it's negative, you have one extra step to do. Yeah? Okay. What have I just done? Got the cat trapped, right? We're trying to get a limit on this guy right here, right? That's all that remained, is to take the limit as h goes to 0, but I couldn't do that limit. But now I've got a function on its left and a function on its right. What am I hoping to apply here?
The average.
No?
The square.
Good guess? What's that?
The square theorem.
Yeah, the squeeze theorem, the sandwich theorem. Yeah, you can call it whatever you want. The sandwich theorem, the squeeze theorem. I would now like to, now that I've got this function trapped in between these two functions, let's look at the limit as h goes to 0 for this one, and the limit as h goes to 0 for this one. So taking the limit of all three sides, we get the limit as h approaches 0 of f of u is less than or equal to the limit as h approaches 0 of 1 over h integral x to x plus h of f of t dt, which is less than or equal to the limit as h approaches 0 of f of v. I claim that this limit right here on the left-hand side, I claim that this limit right here is just f of x. How come? Well, where was u? U was a number inside this interval, right? Where was u? U was this number right here that was sitting inside this interval. As h goes to 0, what does u go to? X. So as we said, one thing I said, hey, don't forget, we're going to keep this idea. Here it is. That's what's showing up right there. I've got a number u. Where'd it go? Where'd it go? I've got a number u that's trapped inside this interval. The interval is collapsing down to just the point x. So if I take f of u, when I look at the limit as h goes to 0, it becomes just f of x. Now I can only do that because of y. What did I say way up here when I showed you this? This only applied for what type of function? Continuous function. So we need continuity twice in this proof. We needed it once for the extreme value theorem, and we needed it once to be able to collapse a function onto itself like that. So this gives us this is less than or equal to the limit as h approaches 0 of 1 over h of x to x plus h of f of t dt. But what does this limit go to? It goes to f of x also. We caught the cat. It's trapped. It's got nowhere to go. What is this whole big expression right here in the middle? That was our difference quotient. Therefore, g prime of x, which is this guy right here, equals what?
F of x.
F of x. There's some smiles in the classroom. I'm trying to hide it. It's okay. That is the fundamental theorem of calculus part 1. It required us to use basically all the tools we've been developing the entire semester. Right? At the beginning of the semester, we introduced limits. Then we talked about continuity. Then we introduced derivatives. Limit definition of derivatives. We talked about indeterminate forms. We then introduced the extreme value theorem. We then played some games. We learned how to take some new derivatives, right? We learned how to take harder and harder derivatives, second derivatives, graphs and things, applications. Then we returned to this new idea of the definite integral, which is an area function. And we just learned that the derivative of an area function is the shape of the underlying function. Da, 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 da. All right. That was the proof. Go ahead and draw yourself a little box and shade it in.